everyone, my name is Arwa Alsaleh. I graduated from Imam Abdurrahman bin Faisal University in Saudi Arabia in 2018 with first class honor degree in chemistry. Now I'm pursuing my master's degree in organic chemistry at Selçuk University in Konya, Turkey. First and foremost, it's an honor to be here with you representing our group of researchers, and I want to express my sincere gratitude to my supervisor, Dr. Arzu Uyanık, for giving me this opportunity. Today I will discuss our most recent study, which involves the synthesis of new fluorescence sensor based on quinaldinium salt, and we are going through an investigation of its fluorescence properties toward specific metals. We designed and synthesized a new fluorescence chemosensor based on quinaldinium bearing an imidazole ring via convening reaction. Subsequently, we conducted an investigation into the fluorescence properties of this new chemosensor using fluorescence spectroscopic techniques. Among various metal ions, our sensor exhibited a remarkable fluorescence response, specifically towards cadmium, zinc, copper, and iron ions when dissolved in acetonitrile. Here I'd like to take you on a journey of fluorescence molecular designing, but first we need to create a previous perspective to understand why the scientific community has a growing demand for practical sensors capable of detecting harmful ions even at low concentration levels. So here we can take a quick glance at what some metal ions could cause with a long time of exposure, and we have toxicity, organ damage, and other damages. Among various detection methods, fluorescence molecular sensors can provide very advantages, just like selectivity and high sensitivity. Despite the mechanism that fluorescence molecular sensors could work with, here we have the simplest conception of the general structure of any fluorescence molecular sensor. So we start with an ionophore, which we can call also the recognition moiety, bond to a fluorophore, the signaling moiety, either with a spacer or not, and the whole system is called the fluoroionophore. Also, in many cases, the recognition part, the part that contributes to the complexation with an ion, could be an atom or a group located in the fluorophore moiety. Therefore, the selectivity of binding often results from the whole structure involving both signaling and recognition moieties. We also should emphasize the interaction between the ionophore and the fluorophore can be explained by various mechanisms, just like PET, ICT, FRET, etc. In this study, we synthesized a new ICT-type fluorescence chemosensor through the interaction between the imidazole ring and the quinaldinium group via convening reaction. ICT-type sensors, including both electron acceptor and donor groups, form a donor-by-acceptor structure. These push-pull sensors exhibit a large dipole moments and strong ICT effects, which could be stabilized by protic or highly polar solvents. Imidazole ring is considered as an electron donor group due to the lone pair of electrons on the nitrogen atom and can form a powerful ICT effect when attaching to a strong electron withdrawing group. Here we have the experimental section, and as we mentioned before, the new sensor was synthesized via convening reaction, which is a special type of aldol condensation. And if we like to examine the mechanism, so we have the base, which is in this case, piperidine will immediately grab a proton from this active carbon, resulting in a negatively charged carbon that can act as Lewis acid and subsequently attack the carbonyl carbon, leading to the formation of double bond in this region. In the HNMR spectrum, we can observe the following peaks: a triplet peak representing the CH3 group, and a quartet peak belongs to the methylene group, shows at 4.9. And then we have the hydrogen atom bound directly to the nitrogen appearing as singlet peak at 13 ppm. And here we have two peaks which belong to the olefin hydrogen, appearing as a doublet at 7.5 and 8.3 ppm. And then we have the peaks that belong to the amidizer ring, appearing as singlet and show at 7.8 and 8 ppm. And here we can see 6 peaks related to the aromatic rings and spanning a range between 7.8 and 8.9 ppm. Here we have the preparation of cations and ligand for the fluorescence measurements. For obtaining fluorescence spectra, the solution of the ligand Qi was further diluted to 10 macromolar in various solvents, and the most suitable solvent found to be acetonitrile. So here we have the concentration of the ligand mix with various metal ion, and after shaking the sample for a couple of seconds, the fluorescence spectra were measured. Here we have the fluorescence spectra of the sensor Qi exhibited a maximal emission at 377 nanometer, and we can see how 13.2 equivalent of the metals interactions can affect the fluorescence spectrum. The spectrum is redshifted from 377 to 419 with an enhancement in the emission equal to twofold due to the interaction with zinc metal ion. The spectrum of the cadmium is redshifted to the same region as zinc, just without the enhancement in intensity. It's well known that zinc and cadmium are difficult to be spectroscopically distinguished due to their similar properties. And when iron ion and copper ions were introduced to the ligand, the spectrum is completely and partially quenched respectively. In order to understand the binding properties of Qi ligand with these different metal ions, the fluorescence titration experiments of Qi ligand with zinc and iron were performed. The fluorescence intensity of Qi increased with the increasing concentrations of zinc added from 0 to 13.2 equivalent, and further addition of zinc did not induce obvious increase in the fluorescence intensity of the sensor. And a nearly linear relationship is obtained between the fluorescence intensity and the concentration of zinc. And for iron ion, the fluorescence intensity of Qi ligand decreased with the increasing concentrations of iron from 0 to 13.2. And the same way here, further addition of iron ion did not induce obvious decrease in the fluorescence intensity, and a linear relationship is obtained too. A competition experiment of iron ion can show that in the presence of other metal ions, Qi sensor exhibited a strong tendency to award iron ion. The presence of other metal ions that might interact the ligand, such as cadmium or zinc, caused no interference to the fluorescence emission induced by iron ion. And this proved that Qi sensor can easily distinguish iron ion from other metals. So, as we have mentioned before, the sensor contains two moiety, the donor and the acceptor, and it's well known that in this kind of sensors, when a group like an amino group playing the role of an electron donor within the fluorophore interacts with a cation, this reduces the electron donating character of this group, leading to a reduction in the conjugation in general. So, a reduction in the measured fluorescence intensity is highly expected. But when cation interacts with the acceptor, that enhances the electron withdrawing character of this group, and the emission might be redshifted and the fluorescence intensity increases. In conclusion, we designed and synthesized a new fluorescence chemosensor based on quinaldinium bearing an imidazole moiety. We investigate the fluorescence properties of the new chemosensor using fluorescence spectroscopic techniques. Among various metal ions, our sensor exhibited a remarkable fluorescence response to award cadmium, zinc, copper, and iron ions. Thank you very much for your attention, and I would be happy to answer any questions you may have.